Here we're told we have 1 kilogram of air in a piston cylinder assembly that undergoes a thermodynamic cycle consisting of 3 processes. We have a process 1 to 2 is a constant specific volume process. Process 2 to 3 is constant temperature expansion. And 3 back to 1 is a constant pressure compression. It's a cycle because we were starting at state 1 and then we end up back at state 1. We're told at state 1 the temperature is 323 Kelvin. We're given the pressure. We're told at state 2 the pressure is 2 bar. And then we're asked to assume an ideal gas equation of state. Sketch the process in PV coordinates, so that's just plotted on a PV diagram. Determine the temperature at state 2, the specific volume of state 2, the heat transfer into the air per unit mass of air. That's what we call the specific heat transfer during the process from 1 to 2. And then what's the change in the internal energy of the air over the entire cycle? So let's go ahead and sketch this out. We've got a piston cylinder arrangement. And we're told that we have air in here. The air is going to be our system. There's some heat transfer that will go into the air, and there's some work being done by the air on the surroundings, since it's a cylinder piston arrangement. So let's first of all sketch the process on a PV plot. So here's the pressure axis, here's the specific volume axis. We're told at state 1, from state 1 to state 2, it's a constant specific volume. So let's call this state 1. So state 2 will be something like this. Let me sketch that out. I'm drawing it vertically because it's a constant specific volume process. So V1 and V2 are the same. And I've drawn state 2 higher because I know that the pressure at 2 is 2 bar. And the pressure at 1 is 1 bar. So I know that the pressure is increasing from 1 to 2. Okay, from 2 to 3, it's a constant temperature expansion. So isotherms on a PV plot look like this. So it's going, let me clean that arrow up. That was a mess. Okay, so here's what an isotherm looks like. So this is temperature equals a constant. The reason I know that is for an ideal gas, we have the following expression. This is just from the ideal gas law. So the ideal gas law. We know that. And so if it's a constant temperature process, then PV is equal to a constant. Or you could write it as this way, P is equal to a constant over the specific volume. So that looks like a hyperbola, which is this kind of curved shape here. It's my best attempt at a hyperbola. So we know that in going from 2 to 3, it's a constant temperature expansion. Expansion means that the specific volume is increasing, so that's why the arrow is going to the right. So it's increasing the specific volume. And then from 3 to 1, it's constant pressure compression. So that means my point 3 should be at the same pressure as P1. So that will look like this. Okay, so this is my point 3. So a constant volume process from 1 to 2, pressure is increasing. From 2 to 3, it's a constant temperature process. It's expanding, so the specific volume is getting bigger. And then from 3 to 1, it's a compression. You can see it's given up here as a compression at constant pressure. So P3 and P1 are the same. Back to 1, so this is our cycle. Okay. So we're given the temperature and pressure at state 1. That's given up here. Let's determine the temperature at state 2. Okay, so we want to find the temperature 2 here. So to find that, what I'm going to do is, if I can find, since I know the pressure at 2, if I can find the specific volume and then use the ideal gas law, I should be able to find the temperature. And the reason I'm focused on specific volume is because I know the specific volume at 1 and the specific volume at 2 are the same. So if I know the pressure at 2, which I'm given, if I can find the specific volume at 2, which I'll be able to find because it's the same as specific volume at 1, then I should be able to find the temperature at 2. So from the ideal gas law, T2 will be P2 V2 all over the gas constant for air. That's, by the way, the gas constant for air. It is not the universal gas constant. It's just the gas constant for air. And to find V2, I'll use the ideal gas law at state 1. So that's V1 will be RT1 divided by P1. Make sure I've got that right. Yeah. And so I know the values for P1 and T1. Those are given in the problem statement right here. But let me just go ahead and substitute this directly in here. I can substitute in there because I know V2 is equal to V1 for that constant specific volume process. So then I'll have T2 is equal to P2 times R T1 all over P1. That's all divided by R. And so you see the R's cancel out, so I don't even need to know that value. So T2 will equal T1 times P2 over P1. So that's how I can find the temperature at state 2. So I know T1 is given, that's 323 Kelvin. P2 is given as 2 bar. Make sure you use an absolute pressure since you're taking one pressure and dividing by the other. That needs to be absolute pressures when you do that ratio. P1 is given as 1 bar. So we can see that the temperature should just double. So T2 will be 646 Kelvin. And by the way, since temperature is constant from 2 to 3, I know that's also equal to T3. Right? So far I've done part A and part B. Let's do part C. Determine the specific volume at state 2. Well, that's easy because we know the specific volume at state 2 is going to be the same as the specific volume at state 1. So I could just simply just do this calculation. So if I do that calculation where I assume, so V2 is equal to V1 is equal to R T1 over P1. Again, I know T1 is 323 Kelvin, P1 is 1 bar absolute. I should convert that over to pascals. Again, it has both. We have to have an absolute temperature and an absolute pressure. The R for air, you can look that up, or it's worthwhile to memorize this one because we use it all the time. But that'll be 0.287 kilojoules per kilogram Kelvin. Okay, that's a number that's worth memorizing because it shows up so often. But if we do that, then we have V2 is equal to V1. These are the specific volumes. That comes out to be 0.927 cubic meters per kilogram. So that's part C. Part D is to determine the heat transfer into the air per unit mass of air during process 1 to 2. So what is the heat transfer into the air as we go from 1 to 2? So to find that heat transfer, I'm going to make use of the first law, because that involves heat transfer. So that'll be the change in total energy of the system is equal to the heat into minus the work done by the system. And the change in total energy of the system will be equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy of the system. We'll assume that for this piston cylinder arrangement that it's not moving, so it's not changing velocity, so that means the change in kinetic energy is 0. And it's also not changing elevation, so the change in potential energy is equal to 0. Okay, so that means that we'll just have a change in the internal energy. The heat transfer is what we're trying to find. The work done by the air in the process from 1 to 2 will be 0. And the reason I know that is because the specific volume remains constant. So that means there is no PDV work that's occurring. The piston isn't moving since the specific volume or the volume just remains constant. So remember, this is from 1 to 2. That's what we're asked to find in the problem statement. So this term will be 0. Okay, so that means then if I rearrange this, we'll have Q into is equal to the mass times the specific internal energy minus at state 2 minus the specific internal energy at state 1. All I did here, this is just the delta capital U. I just broke it up into mass and the change in specific internal energy. The mass, well, actually what I'm trying to find is the heat transfer into the air per unit mass of air. So really what I want to do, let me erase this one. get rid of, just divide through by the mass and just make it Q into over the mass is equal to that. That's what we're trying to find. Okay, now to find the specific internal energies, what I'm going to do is make use of the ideal gas table for air. I know the temperature at 1, that's given right up here as 323 Kelvin, and I calculated the temperature at 2, 646 Kelvin, and I know that for an ideal gas, that the specific internal energy is just a function of temperature only. So I can go to the ideal gas table with those temperatures and determine what the specific internal energies are. So I have portions of the ideal gas table. So this is the ideal gas table, property table for air. And you can see I have the temperatures here. So the T1 was 323 Kelvin. So that's somewhere between these. Let me just focus on the specific internal energy right there. So I know that my specific internal energy will be between those two values, and I can interpolate to find it. If I do that, you'll find that the U1 comes out to be 230.56 kilojoules per kilogram. So that's just a linear interpolation. I won't go through the steps on that. The other one was T2 was 646 Kelvin. So that specific internal energy will be between those two values. And then again, if you do the linear interpolation, that comes out to be 470.12 kilojoules per kilogram. So now we have our U2 and our U1. So we can make use of those up in this equation, and then we'll get the Q into per unit mass. So the heat transfer into the air per unit mass. Sometimes we get that the symbol a little q. That comes out to be 240 kilojoules per kilogram. All right, so that's now our part D. The very last question is, what's the change in the internal energy of the air over the entire cycle? So as we go from 1 to 2 to 3 to back to 1, what's the change in internal energy as we go through that whole cycle? Well, that's actually pretty easy to answer because we know that internal energy is a property, and the property will return back to its original value if we're back in the same original state. So the change in the internal energy over the whole cycle will just be 0, just because we return to the same state. If you need a little more convincing, just keep in mind that, for this ideal gas, for example, the temperature at state 1 is 323 Kelvin, so you'll see that, we'll change to 646 Kelvin, back to 646 Kelvin at state 3, and then back to 323 Kelvin at state 1. So we're back to the original temperature, so that since the temperature is the only thing that matters for the specific internal energy, you'll see we'll get back the same value for the specific internal energy, which means that the change in internal energy will be 0 over that whole cycle. Okay, so I think that covers everything we needed to do for this example. It's a nice example dealing with using the ideal gas law and using the ideal gas tables to get these specific internal energies, a little bit of an application of the first law, and then just recognizing that over a cycle, properties don't change. You always go right back to your original state. And since internal energy is a property, the change in internal energy over the cycle will be 0.